Good morning everyone, I am Rihan Anjum. Currently I am pursuing my first BTech in Srinivasa Ramanujan Institute of Technology in Anantapur. Now I am going to discuss about direct and indirect band gap of semiconductors. So now let us see the introduction to band gap of semiconductors. Band gap means the distance between the conduction band and the valency band. Here right side of the slide you can see there are three diagrams of band gap semiconductors. One is insulator, semiconductor, and conductor. Uh, in insulators, there is a large band gap between the conduction band and the valency band. In semiconductors, there is a minimum band gap between the conduction band and the valency band. And in conductors, there is no energy gap between the conduction band and the valency band, which means they are overlap each other. And these energy gap plays a crucial role in determining the electrical and optical properties. The difference between direct and indirect band gap semiconductor is essential for various applications in electronics. Now let us see what is a band gap. The gap is the energy difference between the highest occupied electron state and the lowest occupied electron state, which is nothing but conduction band and the valency band. It determines how a semiconductor interacts with the light and how it conducts electricity. Semiconductors can be classified based on the nature of their band gap, which can be either direct or indirect. Now let us see the direct band gap semiconductors. In direct band gap semiconductors, the maximum of the conduction band and the minimum of the valency band occurs at the same momentum. These alignment allows for the efficient absorption and emission of light, making them ideal for optoelectric devices. Here you can see in the diagram direct band gap semiconductors. There is a energy gap between the valency band and the conduction band. The maximum of the conduction band and the minimum of the valency band both occurs at the same state, same momentum. And the examples of the direct band gap semiconductor is silicon and germanium. Now let us see the characteristics of direct band gap semiconductors. Direct band gap semiconductors can easily emit photons when electrons transmit from the conduction band to valency band. They are widely used in light emitting diodes, which is nothing but LEDs, and laser diodes due to their efficient light emission capabilities. The efficiency of light emission in direct band gap materials makes them preferable for many photonic applications. Now let us see indirect band gap semiconductors. Indirect band gap semiconductors or the maximum of conduction band and the minimum of valency band occurs at the different momentum values, and these requires a phonon interaction for the electron transition, making light emission less efficient compared to direct band gap materials. You can see in the picture in indirect band gap of semiconductors, the maximum of the conduction band and the minimum of the valency band are different momentum values. And silicon and germanium are the examples of the indirect band gap semiconductors. So these are the commonly used in electronic devices. And let us see the characteristics of indirect band gap semiconductors. Indirect band gap semiconductors are less efficient at emitting lights, which limit their use in photonic applications. However, they are widely used in electronic devices due to their excellent electrical properties and availabilities. The ability to manipulate their electrical properties makes them suitable for applications in transistors and solar cells. So these are the characteristics of the indirect band gap semiconductors. Now let us see the applications of band gap semiconductors. Direct band gap semiconductors are primarily used in optoelectronic devices like lasers and LEDs. Their efficient light emission capabilities makes them ideal for communication technology and displays. They are also used in photovoltaic applications and converting solar energies into electrical energy efficiently. Now let us see the applications of indirect bandgap semiconductors. Indirect bandgap semiconductors are predominantly used in electronic devices such as transistors and diodes. Their properties allows for effective charge transport, making them suitable for integrated circuits. Additionally, they are used in solar cells, although their efficiency is lower than that of direct bandgap materials. And the key difference between these bandgap semiconductors are direct bandgap semiconductors allows for direct photonic emission, leading to efficient light generation. Indirect bandgap semiconductors requires photonic interactions, making light emission less effective. Each type of semiconductors has its unique advantages and applications, influencing technology development, which we had seen in our previous slides. And the future trends in bandgap semiconductors are research is going to explore new materials with tailored bandgap properties for enhanced performance. And technologies like two-dimensional materials may bridge the bandgap between direct and indirect bandgap semiconductors. And semiconductor technology will likely revolutionize electronic and optoelectronic devices in future. So these are the applications, advantages, introduction to bandgap and direct and indirect bandgap of the semiconductors. So thank you for this opportunity.